Uh, Many of us know how DLNMs work. We have used them or, in any case, read about them. DLNMs is the most widely used and sophisticated method in researching environmental epidemiology, health impacts of various environmental stressors, and this 3D graph is the most classical representation of DLNMs. However, in our case, when we begin about 2 years ago, our research in studying the synergistic impact of various environmental factors on health, we discovered that DLNMs have some inherent restrictions that challenged our case. You may know that in DLNMs you have to manually select the model and then validate it using many criteria we have in hand. And the DLNMs also are very prone to overfitting, to over-explaining data and extending the relations to the outliers. And the third disadvantage that in our case was the most important one is that DLNMs lack a consistent way to study the synergistic effect of simultaneous environmental stressors on human health. So given these restrictions, we were obliged to find another way to use DLNMs without these disadvantages. So what we did was we used this established framework, but we extended it into the machinery of a different statistical model using the machinery of generalized additive models. By using this, we combined the advantages of these two models, exploited the best points of each. So using DLNMs, we were able to describe flexible and time-varying effects and also use the very appealing visualization of DLNMs, their excellent graphs and curves. And using the machinery of GAMS, by using the machinery of GAMS, now we didn't have this inherent bias of manually selecting our models. And by making optimal, by penalization and smoothness, we made optimal use of our data. In addition, with Bayesian inference, we were able to quantify the statistical significance of our results, and we illustrated the uncertainties with two-dimensional raster images. Just to have an overview, this is one equation that describes the simultaneous exposures from apparent temperature and exposure to various PM10 levels. And these exposures are stratified in different lags along the temporal dimension. And all these exposures have a certain outcome on health, in our case, with the daily mortality. And this three-dimensional surface is the conceptual way we came up with in order to show how we extracted from the four-dimensional relation, which is the apparent temperature, the pollution, the temporal dimension, and the mortality risk. From this four-dimensional association, we extracted this three-dimensional surface in order to show conceptually the way that we worked. In terms of interpreting our results, we quantified the relative risk, which is the mortality effect, and it shows the likelihood or probability for a certain group of population to suffer from the health effect that we are studying. In our case, it was death. And of course, we know that depending on the values that relative risk depicts, it shows if we have a mortality risk or a protective effect. And then we quantified the mortality burden, the attributable in terms of attributable mortality fraction. The physical meaning of attributable mortality fraction is that it represents the expected reduction in mortality if the exposure that we're studying was eliminated or never existed. So with these two quantities, statistical quantities, we were able to study the synergistic impact of thermal stress and pollution on human mortality by two different scopes. And very quickly, these graphs were presented in Monday session, so I will not go through them again. We have the 3D relative risk surfaces. We also have the two-dimensional cumulative relative risk. As I said, we have depicted the uncertainty by showing with gray areas the 95% confidence intervals. We have also quantified the heat and cold effects on mortality stratified by different pollution levels, low, medium, and high. We have also quantified the mortality burden for different ranges of non-optimum apparent temperature, and again stratified by different levels of pollution, either PM10, ozone, or NO2. These were the pollutants that we had in our dataset. And last, apart from all-cause mortality, we were also able to examine cause-specific mortality in terms of cardiovascular mortality, CVD, mortality RD, and we also analyzed the age group 65 plus, which was named elderly in our analysis. Then the most interesting thing I think we did in our analysis, and as far as we know, it hasn't been shown in any other similar study, is that we specifically analyzed the lag dimension of our associations. We were able to do that by quantifying the cumulative relative risk in two different cases, along the environmental risk of apparent temperature, and then along the second environmental stressor, along pollution. So in the first case, when we cumulated the relative risk along the apparent temperature for the three pollutants we studied, PM10, NO2, and ozone, in all three cases, you can see that we reproduce the classical J-shaped relations evident in many cases in relevant literature, which mean, as we may know, that the heat effects are very are happening on the day of the exposure, are rather immediate, while the cold effects take about, in our case, 1 week or even more to accumulate a significant health effect. The second case, when we cumulated the relative risk across the pollution range, PM10, NO2, and ozone, we saw very interesting and distinct behaviors when we moved from one pollutant to another. In the first case, PM10, you may see that the maximum relative risk, cumulative relative risk values are evident for today, for the day of the exposure. So this means that regardless of the PM10 concentration we're experiencing, the relative risk is maximum on the day of the exposure, and it diminishes as time goes by until lag 6, which is a week after the exposure. In the case of NO2, the behavior is exactly the opposite. NO2 needs more days to accumulate the health risk, and the maximum relative risk values are evident for 1 week after the exposure. So NO2 needs more days to bring an impact on human mortality. And in case of ozone, ozone was the most complex than the other two. We see there that there is a distinct threshold at about 150 micrograms per cubic meter ozone concentration. And we see that below this value, this threshold, the maximum relative risk is for a week later after the exposure, while for the high concentrations of ozone, above 150 micrograms per cubic meter, the health effects were immediate, were happening at the exact day of the exposure. And this result was very interesting, and it kind of emerged in another analysis we did for the same population, namely the population for the urban area of Thessaloniki. And last, we met a problem. When analyzing populations that are not large enough, like a Thessaloniki's urban population or the population Cyprus, in this case, we had a problem. The statistical power of our data sets was not very high. So the statistical models cannot very very clearly see the relations we are trying to see. In the case of Cyprus, Cyprus consists of 5 regions: Famagusta, Larnaca, Limassol, Nicosia, and Paphos. When we tried to see the temperature mortality relation for these 5 regions separately, we couldn't extract results that made sense. That was not very logical because, of course, each region should have a distinct relation. But when we looked into our data set, we saw that mortality had many 0 and 1s. So we thought that the model masked the results behind these zeros and ones, and it could not see clearly. We had to find another solution for this problem, and the solution we found is that we moved on to a hierarchical structure of our model. This means that in our equations now we have a so-called global term, which in this case, in this example, corresponds to the entire island of Cyprus, and this is the global term. On this global term, this methodology allows for unit-specific effects to describe the distinct behaviors of these 5 regions that make up Cyprus. So with this methodology, we exploit both the city-specific, the region-specific relations that we were trying to see, but in the same time, we found a way to face the problem of low mortality count data. And this methodology can be extended in order to study not only specific slices of regions within the initial dataset, but whatever slice we try to decide to see in our original dataset, namely different population groups or cause-specific mortalities, or make a seasonal analysis, or whatever. So this extension of our original methodology applied to see various slices of our initial problem. This specific case is being published, is under review in the journal Statistics in Medicine by our colleague Theo Economou. And just to sum up, the novelties of our framework is that we exploited the strengths of the LNM and we combined them with the strengths of GAMS. And it was, as far as we're concerned, the first time that we were able to show such a detailed temporal analysis of the 4-dimensional associations. So we were able to show and apply a consistent method to study the synergistic impact of various exposures on health outcome. And regarding the hierarchical structure of our model, we are able now to pull information across distinct units of our dataset, and this is very important as well. We now can provide robust estimates of the covariate lag effect for each level of the district units. In case you're interested, this is our work under publication or already published, and we're always very interested in hearing your thoughts. Thank you.